Welcome to our presentation about the use of state tree for the implementation of the AI of the survival game Gunner. I'm glad to see there's a good interest in state tree. So let's go over it. So my name is Corentin Lemasson. I am a lead programmer at Black Shamrock for 4 years now. Before working on Gunner, I worked on action RPG, an unreleased action RPG for 3 years. I mainly specialize in gameplay and AI programming.
Howdy everyone, my name is Florian Peters, and I've been working at Black Shamrock for 2 years as a software engineer, where I've been honing my skills on mostly gameplay and AI programming.
Black Shamrock is a studio located in Ireland. We provide co-development services to the studio to try to make their dream game come true. Black Shamrock is part of Virtuos, which is a group with studios all over the world with different areas of expertise and a good match with time zone to have a better communication with developers. The game we worked on, Gunner, is a single-player survival game developed in Unreal Engine 5. It is still in development right now by local players, a studio located in the Canary Islands with Tate Multimedia as a publisher. When we started to work on the game, there was already a lot of development that went into it, about 2 to 3 years. And they already started to implement the AI using behavior tree. The problem, and maybe some of you experience it, is that behavior tree can be quite hard to debug. So the decision we took, because we had a good experience in using state tree, is to move the development to state tree. And that's what local player and Tate Multimedia agreed for us to do and try to make the AI successful.
So first, let's talk a little bit more about Gunner as a game and the project requirements. So the game features a large array of diverse species of fauna with a large range of scales, going from a tiny, small Richardoestesia to towering Alamosaurus, which can range to 20 meters height. The game also made use of the Mercuna navigation plugin, which allowed us to create different navigation grids for the different sized dinosaurs. Different scales implied the need for a flexible animation system, so we would need to play animations for similar actions, but with drastically different visuals and length. It is also important for the game's intention that the player feels like a part of a larger ecosystem. And that's why we have a bunch of wildlife simulation systems in place. Basic needs like food and water play a huge role in making those animals come to life, which is why they get thirsty and hungry, and they need to go and get food sources across the map to generate organic interactions between those species. There's also a system for managing the diet of the dinosaurs, which is why we have a predator and prey system. So when they get hungry, they will start predating on different kinds of species, depending on their diet. There's a day-night cycle for the gameplay, so the dinosaurs can go to sleep at night. And there's a bunch of other additional systems as well to make this come to life. So we have dinosaurs becoming more aggressive in group. They need to defend their nests, and they also fear any kind of fire sources. And all those systems come together to help make the world feel real and believable. Combat is also an important pillar for this game. It is a real challenge, both for the AI and the player. In terms of AI, it indicates that there's a need for good positioning because the animations need to land at the correct positions. And for the player, it's very risky to go into combat, especially in a survival game. So we have to essentially use the various perception senses of the AI to allow the player to potentially escape those dinosaurs. So they would rely on sight, smell, and hearing, and they would not get any global positioning of the player at any times. Let's talk a bit about the high-level problem that we're trying to solve here. So roughly what we have is the following. There is a game world, and in that game world there exists an agent. That game world produces a context, which is a stream of data that is fed into this agent. The agent then, based on that context, decides what sort of action it wants to perform on the game world. And this cycle repeats itself up until the agent is not active anymore. The problem of going from this context to the chosen specific action has been solved or tackled using different techniques over the years. Some of you might be familiar with them. They consist of finite state machines, behavior trees, GOP, HTNs, etc. In Goner, we decided to switch from the behavior tree system to a state tree, since we had experience with both systems, and in this particular case, we could see the clear advantages of state tree over behavior trees. And we're going to expose those in the following section.
So what is state tree? It's a framework within Unreal Engine that can be implemented in our case, used to implement in our case complex AI behaviors for agents. But as I discovered during the Unreal Fest, it can also be used for any kind of use like animation. It combines the advantages of like finite state machines with the states and the transitions with in combination, the hierarchical aspect that behavior tree provides. State tree is kind of new. Well, it starts to be a couple of versions it's in now, but it starts to be really production ready since 5.3. And it can be challenging to start with because it's difficult. There's not that many examples, and the documentation doesn't give all the details. On screen, you can see the editor for main state tree assets, with on the left the parameters of a state tree that can kind of accumulate after some time for a big game. In the middle, you can see the hierarchy of states with the root states and a few children states. And on the right are the tasks that are on the state currently selected, in this case, the root state. So let's go over how it works and how it differs from behavior tree. So as I said, it's built as a hierarchical states that can be active at the same time. So in this example, you can see that all the states highlighted in yellow are active at the same time. So the root state, aggressive, active, down to the normal attack state are all active at the same time. So that means that all the tasks that are on those states are going to run at the same time. Compared to behavior tree nodes, the tasks are much easier to implement, and there's no distinction between tasks. They all can do actions and generate data. It's easy for any task to produce data, and for any other tasks that comes after to consume it thanks to data bindings. There's also a clear scope for the data produced. So that means when you try to select the data to consume it, it's only going to show the data that was produced before. So that's a huge improvement over blackboards, where the data, you never knew if it was valid at that point, and if you could use it. Here, the editor makes sure that you don't make that kind of mistakes. Here we can see that the isFirstC task is going to produce a Boolean that the shouldDrink task is going to consume. Finally, there's the transitions that are quite easy to define, and it provides a great control over how the state tree is going to execute in the end. It's easier to follow compared to the constellations of behavior tree branches. In behavior tree, there was like three constellation policies. Like one was lower priority, same node, both, and it was difficult for developers to know why their behavior tree suddenly switched to another branch. We provided the system to designers, and in one case in behavior tree, they were like, I don't know what's going on, why it's failing. Well, for state tree, they quickly managed to prototype, the same designers. So that really shows the power of state tree. In this example, we've got a transition from the active state that is executed on tick. And this is in the editor and here in the debugger, and we can clearly see which transitions are going to be active at the same time, why they fail or why they succeed. So let's summarize the differences between behavior trees and state trees. Behavior trees is a well-established system. It has been there for since the start of Unreal Engine 4, and it is well documented. It provides a toolbox that has got all the tasks that you could need to start making your AI, and you don't have to have some overhead before getting started to prototype. It has got a very good integration with the environment query system that is very important for AI, like trying to figure out from where an agent is going to try to attack the player, and this kind of thing. Debugging, as I said, can be quite tricky because you've got the behavior tree debugger, but from my experience, developers struggle more to debug behavior tree rather than state tree. And blackboards is difficult to use because you declare all your data from the get-go, and then you have to initialize it as you go through the branches. The thing is that you never know when it's going to be valid. Compared to that, state tree tasks are relatively easy to implement. We're going to see in the following slides how to implement one. The data binding is a really robust system and quite performant. It allows to know which data you can use at any point and to easily share it between tasks. And debugging the transitions is straightforward. The only problems, but it's getting resolved by Epic through the different releases, is that there's few resources to learn from, and there's not that many tasks available out of the box. There's a couple of tasks made for mass entity, but there's none for using just for actors. I think, if I don't mistaken, in 5.4, there's still 2 tasks, like delay and another one.
Right, and now we'll go over specifically how you can create your own state tree task in C++. So the one main concept you should understand about state tree tasks is that they're made out of 2 structs, 2 use structs, in fact. First, we have an instance data, which can be defined as follows. As you can see, it's a very plain struct. It's not inherited from anything. And in it, you just define the data that you want to use for that specific task as your properties. There's 3 categories you got to use. There is the input, parameter, and outputs. Output variables have to be bound in order for the state tree to compile. If you don't bind any of those, the state tree will just simply not run, or compile even. Parameters can be bound or set directly in the state tree tasks. So if you want to set them to any particular value, you can. Or you can rely on an earlier task in the state tree to bind to. For the output, that's basically what it is. It's just an output that you can bind later on in other tasks of your state tree. In this example, we can see that we have 3 different types of instance data. We have a t-object pointer to an actor, a float parameter, and finally a vector output. And in the editor, this is what this would look like. So as you can see, it's very straightforward. There's no particular surprises there. The little button with the down arrow is actually where you would bind those particular parameters or inputs. The second struct that you need to define your state tree task is the state tree task node itself. This one actually inherits from a common base called f state tree task common base. And you can give it a fancy display name because otherwise you will get the auto-generated f state tree tasks underscore and a gigantic line, which you don't want to show your designers. You want to make them very friendly. And in this case, the first few lines of code you're going to add are those override for the get instance data type. That one will actually link the instance data struct that we defined earlier to this task node. And then there's 3 main methods you will want to override, most likely. There is the enter state, the tick, and the exit state. So the enter state is essentially your setup phase. So this method is called whenever your node that this task is attached to is first entered. Let's take an example. If you have a state tree task that manages smart object slots, for example, this is what you would try and reserve that slot. In the tick method, this is just the ongoing tick of your state tree tasks. It's called every single tick as long as the node is active. And finally, the exit state, it's called when you exit the node that this task is attached to. Very simple. In our smart object example, this is where you would perform the cleanup. So you would release the smart object slot at that point. And let's give you a very quick example of an actual state tree task that we use. This one simply generates, it's going to be a data generator. It's only going to output the direction vector between two actors that you provide. So as we can see in the instance data, there is the two inputs. So we have the origin actor and a destination actor. And the other U property that we define is the output, which is simply the direction vector. At the bottom, we can see that we've only defined we've only overridden, the enter state and the tick. That's because in this particular case, we don't need to perform any sort of special cleanup for the task. Note also that we have a private internal function called refresh direction, and that's going to be used by both the enter and tick functions. In the CPP file, this is what we will have. So like I said, the enter state and the tick functions have the same exact code inside of them. There's the refresh direction, and it returns that. That's it. There's nothing fancy there. And the internal refresh direction method, we simply get the instance data from the context using the context.getInstanceData. And after we verify that the origin actor and the destination actor are not null, in which case we would just simply return fail. If they're not null, though, we just simply get the unit direction vector from that as nothing fancy, and we place it in the direction output vector. A couple of things to note here. You'll notice the trace CPU profiler macros there. So those are particularly helpful if you want to optimize your state tree tasks. So this will create specific traces in Unreal Insights, so you can fine-tune, identify where your bottlenecks are in your state trees. The final thing to note is that you notice that we're not returning, on success, we're not returning succeeded at the very end of refresh direction. Why is that? Well, that's for a very simple reason. If you would return succeeded, the state tree task would consider itself done, and it would exit. So we don't want to do that. We want to continuously generate that data over and over again, which is why we're just returning running in this case. And that's it for the task. Nothing more, nothing less. We find that the more compact and direct you keep your state tree tasks as small, tiny Lego blocks, the better. Because then you can combine those different tasks to create entirely new complex behavior out of that. So now that we've seen how to create state tree tasks, we have to mention that state tree, while a great system to define new AI behaviors, it does not provide a way to handle higher decision making. Which is why we had to find an efficient way to define which actions to take based on that context. In our case, we have an input, so the context is coming from Unreal Engine's AI perception system, and it's handling all the senses that an agent has. So in our cases, it was sight, hearing, smell, and touch. And based on the stimuli, we want the AI to react differently. But there are a lot of different stimuli, and we want to make sure that the AI doesn't oscillate trying to react to all of those at the same time. Therefore, we needed to sort them and find out which of them is the most important one to react to. And this was done through our custom perception stimuli sorter. And that one is defined as a series of steps, as a pipeline, to which you feed your stimuli. And it will essentially score all of them and figure out which of them is the highest priority one. Finally, that highest priority stimulus is then fed to our state response selector, which finally chooses the state response. In the actual state tree, this is what we will have. So you can see at the root node, here selected, we have two of those tasks that perform the perception stimuli sorting and the state response selector right here. So let's dive a little bit deeper into how this perception stimuli sorting is happening. So it's implemented as a state tree task, like I've said, defined as a pipeline of actions, which in our case are instance objects, to be very specific. We'll take an example with 4 stimuli. we have here a sight stimulus from a neutral actor, a touch stimulus from an ally, a smell from an ally, and a hearing from a hostile target. So the first thing that we perform is a filtering step. So we take all of those stimuli and we look at different conditions and we figure out which of them we simply discard to optimize a little bit the code later on. In our case, we simply discard the ones about allies since we don't have any particular reaction to take when there's an ally stimulus. The second step that we take is a score and sort. So for each of those stimuli, we're scoring them according to different criteria. So you would basically define one for, let's say, how aggressive the target is, how far it is from me, etc. And you can define all of those as separate scores. These scores are then aggregated into a scoring aggregate vector, which is then used to generate the final ranking of those stimuli. And in our case, here are the following example aggregate scores. And we can see in this case that the hostile stimulus is selected as the priority stimulus. In practice, in the actual state tree that we use, this is what we have. So in blue here, you can see the filtering step, which in our case only consists of a filter by expiration. So if a stimulus is too old, it simply gets discarded because it's no longer relevant to our agent. And then in orange here, we have all the scoring steps, and finally the sort at the end. So all of the sort scores are, they generate a score each. You can see there's one for team attitude, threat level, age threshold, and a sense index. I'll mention a few. So the threat level one is specific to this project. So it was essentially an objective value of how threatening a dinosaur is in the food chain sort of thing. So if you had like a tiny Richard, you probably don't want to react to that. Whereas if there's a giant T-Rex next to you, that's probably the one you want to worry most about. And we have also one for sense index. So that means that if you simply hear a target, but in that same tick you've seen a target, it's probably more important to react to the scene rather than the hearing. And once that's all sorted, we have the bindable output at the end, which is our highest priority perception stimulus. And that's bound later on in the state tree task for further processing and reaction.
Once we have sorted the perception stimuli, we can try to decide what the agent is going to do. To do that, we execute a pipeline of action that is similar to how we sort perception stimuli. The first action in the pipeline is to append all the states that the agent can transition to. And the next actions in the pipelines are going to progressively filter those states till we get the one that the agent needs to transition to. Here you can see that the sleep state is not active because it's not nighttime, similar to the eat state that is not active because the agent is not hungry. Some steps will always be available and provide like a fallback for the agent to turn to, like the roam state and the nest state. And we've got this search state that is going to be active because we just heard an hostile in the previous example. So that gives us our final list of states we can transition to. As we go through those states, we're going to store for each target actor, so for each actor detected, we're going to store which state is associated with it. What it allows us to do is to transition from like a state where we search for the actor. Then we start to like see the actor, and we can start to like transition to a state to attack the actor. Now that we've got the states we can transition to, we're going to try to do those transition requests. Each state has got a priority and a weight. So what we're going to do is to sort these states by priority first. And then we do a randomization based on the weight so that we can have like a list of potential state ordered. So after that, we generate transition dynamically. starting from the first one that has got the highest priority. The names of the transitions are what Unreal provides us. So first a critical, then a high priority, and then a normal priority. And if we've got conditions on those states, enter conditions, if, for example, it fails to enter aggressive because the state has changed slightly, or like there's a designer that has added a condition specific for that state, then it still has a fallback to transition to. And because we are sorting all the perception stimuli, we potentially have multiple actors we can attack at once, ordered by priority. And as we saw in the previous state, it provides the perception stimulus, so we're able to like give that to the actual state so that it can do its behavior. In the case of aggressive, just like move towards the actor and attack it. And this is how it looks like in practice, so very similar to the perception stimuli sorter, where we've got a list of instance objects, and we're going to execute them one by one, starting by appending, and then like filtering by conditions. What we could do next is to maybe improve the system, because right now the weights are actually static. We could do something similar to utility AI and try to calculate like a dynamic weight depending on the context. While the decision making is important, we also need at some point for the actor to do something. To do that, we need to create, what we did is to create like a toolbox of tasks that we can use that are generic enough so that we can combine them in different ways. Some of the tasks that you could create are tasks to move the actor. There it's going to depend on which navigation system you're going to use, if you use the one that is native to Unreal, or if you use, for example, Mercuna. You will probably want another task to rotate the actor, to turn towards the target, for example. And then other tasks that can be useful to create is one to play an animation montage and wait for it to end before it can go towards other task. And also another one we found very useful is to this concept of animation states. You set a state that the actor is going to be in, and then you let the animation blueprint do its logic. So for example, you can set it to be in idle. Maybe it's going to play like 2, 3, 4 random idle before exiting that state. The animation blueprint is going to exit the state. And then it's going to be able to transition again to another state in the state tree.
So another category of tasks you might want to implement are what we call interfacing tasks. So those tasks are essentially wrappers around other systems of Unreal. So in our case, we found it useful to leverage the capabilities of the game playability system, the EQS, navigation system, be it Mercuna or any like the native navigation system, and smart objects in our case. The final category that we found useful was meta tasks. So meta tasks directly influence the flow of logic in your state tree. So they can, for example, we had one called run state tree, which was able to run a state tree within a state tree. This is now supported natively in Unreal. You don't need to do any kind of magic with it. You just need to define your linked asset, and that will run an external state tree to your state tree. You might be wondering, why would I want to run a state tree within a state tree? And that's for a very simple reason. Your development effort might be fragmented across different behaviors. So prior to Unreal Fest, we didn't have diff tools for state tree. So that's coming in 5.5, as we've heard at the 5.5 demo. And it's going to make it a bit useful, accessible. Running different state trees is actually so that you can simply have one behavior that's handled by one developer and another behavior by a different one without stepping on each other's toes. And even more so, you can reuse logic in different parts of your state tree. So if you have one that's just simply moved to a target, you simply define a new state tree, and you can run it in multiple places in your bigger state tree. Other tasks that we've implemented were the send state tree event, just to send a generic gameplay event to your state tree and be able to react to it in another part of your state tree. So this was useful for us when we were running a child state and we wanted to make the parent react, and that's how we did that. Finally, we had the block and replace transition requests. That can be useful when you're performing an animation and you don't want your AI logic to kind of go out of sync with the animation. So you need a way to prevent those transition requests from happening while the animation is still finishing. So if you want to know more about state tree, here are a couple of resources from Unreal Engine 5 documentation. There's a few that you can look at your own leisure. And yeah.
All right. Thank you. Thank you, everybody. And
Thanks so much.
have a good day.